Thank you. So hydraulics, we will be talking these are very common in industry. That is, if you work for a company, you will probably be, either using or monitoring some kind of hydraulic system in your business. If you work in mechanical engineering. First of all, these devices use oil as the working fluid, and oil is incompressible. And finally, again, it's used with high pressures. When I say high pressures, it's like something like 1,000 atmospheres is not uncommon. Okay, so very, very high pressures are used. Well, actually, we have courses in fluid power. Well, there are courses. We don't have it here, but it is possible to have fluid power. So it is a large subject, so I will just give a very, very brief review of it with some very simple devices. Okay. One device that is used in hydraulics is the piston. Which is this. Let's say that you have a hydraulic circuit like this. This is a very, simplest of all devices is this one actually. And it's quite easy to understand. It is sealed here at these ends so that there is so there is oil here. This has a piston, has an area of A and a mass of M, let's say. So there is pressurized oil here with a pressure P. Now this piston experiences oil comes in from here by Q, let's say. This is F. And the piston displacement is, let's say, is X. Okay. Well, there is this is the hydraulic piston. You use it in order to create, move this mass. It is not the mass you are moving, but usually this force F comes from another source, which is like a crushing machine, a machine that is a construction machine or something. So the piston can exert very high amount of forces through the pressurized fluid. And the pressurized fluid is usually pressurized by a pump, okay? So that you can apply very, very high forces, very high amount of forces using hydraulics. Well, the equations are quite simple. If you sum up the forces on the mass, if you look at it, on this piston mass, let's say, the forces are as follows. There is the force of pressure times the area, and there is the external force F. Well, if the piston mass is negligible, you can set these to equal to each other. But if the piston mass is not negligible, in that case, you should write like mx double dot. So sigma F equals ma, which means that this is the positive direction. PA minus F equals mx double dot is the equation that describes the system. And if m is approximately 0, which means that it is small, okay, you can say that PA is approximately equal to the F. Okay, so this is the equation, but there is one more thing which is important. This is the force balance. There is also the continuity equation, which says that the fluid coming here, fluid, by the way, is it is like meter cubed per second. It is the volumetric flow rate. Okay, the fluid coming in should be displacing the piston an amount as it comes in, the same amount. So the Q will be equal to Q coming in should be the Q that moves with the piston, and that is area times dx dt, or area times x dot, okay, ax dot. So both of these equations should be satisfied. This is 1, this is 2, okay? You might, neglect the x double dot term if the acceleration is small or if the mass is small. But you cannot really neglect this Q equals Ax dot. This is essential, assuming that the fluid, the oil is incompressible. I hope you understand this. This is the flow rate is equal to the displacement of the piston. Okay, the rate of displacement of the piston is equal to the flow rate coming in to the piston.
Hocam,
yes.
May I ask a question?
Sure.
It just looks so similar to damper systems. So why can't we just write it as bx dot or something?
You mean this equation looks like a damper, right? The second equation.
No, I mean the whole system just looks like damper. There is some viscous oil.
Not really. There is not much dissipation here. There isn't any dissipation, so it is not a damper. But you can create a damper out of a piston. I will come to that in a while. Okay. Actually, yeah, I will explain that in a while. Okay.
Okay.
It will be very similar to a damper. What we will be doing. But this is itself is not a damper, okay? There is no dissipation, we assume. There has to be some sort of resistance that dissipates energy in order to have a damper. Okay. The second device is the hydraulic cylinder, let's say. Or hydraulic, no, I shouldn't say hydraulic cylinder, sorry. I should say hydraulic servo motor, let's call it. That's it. Now, what does this mean? Now, I, usually spend drawing this, a lot of time drawing this, but now, unfortunately, we have the drawings here in the book, so I will just copy it. Let me see if I can do that. Okay, something like this. Now it looks strange, of course, if you look at it like this. First of all, this is a hydraulic device that moves. Let me write here. This is a device that large loads with small inputs. How does it do it? Now you have a very small input, let's say X is usually your input, okay? And Y will be your output. And let's say that you have a small, large mass connected to this. This is M. So this mass moves with a displacement of Y. And what are all these things? So X is our input, Y is our output. Okay. I wish I could make this a little bit larger, because I cannot any longer. Maybe I can do it like this. Okay. So we have the main piston here, which moves, and on one side of the piston there is P1. On other side of the piston there is piston P2. Sorry, pressure P2. This thing is called the pilot piston or pilot valve, and there are the ports. These are 1 and 2 are the so-called ports. Okay. So what does this thing do? This thing, PS is the pressurized fluid coming from the PS comes from the pump. So PS is the pressurized fluid. Pressurized oil, let's say. Okay. So it is in between those two ports, between those two pistons, the pilot piston. Okay. So according to the movement of this piston, pilot piston, it either goes through the port 1 or it goes through the port 2. For example, if the motion, let's say, is like, let's say that this is the piston and this is the port, like here. So the piston opens the port a little bit. Where this is the pressurized fluid, PS goes from here. This is port 1 and goes and creates pressure P1. There is a little bit of drop, of course, here. Q1 comes from here and pushes this piston, this main piston. Actually, I should learn how to draw this. This is P2. And then, on the other hand, this thing is moved, this is P1. P1 is greater than P2, so this moves in this direction. And the flow, the fluid in this direction now comes Let me draw the second one also. Here it will be like this. I don't know whether I could make it understood. This part, these two pistons are connected to each other. This moves with X, and this piston moves with Y. Okay. So the X motion of the piston opens a port for very pressurized fluid to come in and push P1, push the other piston with an area of A, let's say. And then this moves in this direction, and the pushed piston displaces the fluid and lets P0, lets the fluid go to P0. And P0, P naught is, unpressurized oil, let's say. Is this understandable? Did you understand it, or is it unclear?
Hocam, could you please repeat it?
Excuse me?
Can you please repeat the explanation for this, please?
Sure. It's, you know, at first sight, it's not very easy. It is, you have a input is X, okay? Well, there are two inputs actually. One input is our X. We just move this pilot piston. The pilot piston is easy to move because the pressurized fluid PS comes from this direction, and it pushes the both ends of this pilot piston. So it doesn't apply a net force on the pilot piston. Do you understand? So it is very easy to move this X with a very low amount of force, like, you know, with your finger you can push it even. It's not hard to do. When you push this thing, the pressurized fluid, like, which is in the, in the range of hundreds of atmospheres, goes through the ports, goes through this port. You open the port a little bit, and the pressurized fluid goes and pushes this main piston to move it with a motion of Y. And usually you carry a heavy load by this piston, like this capital M. And when you push it, at one side the fluid comes in, like here, okay? At one side it comes in, and it pushes the piston. On the other side, the fluid on the other side of the piston at P2 goes and gets out and goes to the hydraulic circuit again to be cleaned and to be sent to the pump again. Do you understand this?
Yes, Hocam, thank you.
So when we move the piston, in the ports, if it's in equilibrium, if X is 0, both ports are closed. If X is, increased a little bit, what do you do is, if you look at this port like this, let me draw it in a better way. Like, if this is the port in 3 dimensions, if you move it like X here, this is the X motion, okay? There is the piston at the top of it. You open this an amount of X. So X, this is, and the fluid goes through here. flow of Q, let's say. And this thing, let's say that this thing has an area of, well, let's say it has a width of W. So the area that which the fluid goes in is, let's say, area 0 is W times X. So the area of the fluid going in is proportional to the displacement X. On the other hand, if you move X in the negative direction, what happens is you don't open the port 1, but then in this case, if you move the X in the opposite direction, you open the port 2, okay? So the pressurized fluid goes from the second port and pushes the piston in the opposite direction, okay? So in that case, for negative X, P2 is greater than P1 and the piston moves towards the right, not towards the left. As you see, we have defined positive values for X and Y. X is towards the left is positive, and Y is towards the right is positive. Because when X moves towards the left, Y moves towards the right. Do you understand this? Okay. So this is the working of the pistons. What is the net result? With a very small input of X, you can move very high loads of Y, okay? You know, the Y is might be connected to a very, very big load of M. How do you do it? You do it by the use of this pressurized fluid PS. This is actually another input, actually. This is also an input to the system, the pressurized fluid. But you don't have the control over it. It is done by the pump. What you do is you control a very high amount of fluid, very high power fluid, by a very small input X. You know, as I have said, with the tip of your finger, you can control tons of loads. You can move tons of loads. So this is actually, you might call it if you want, sorry, hydraulic amplifier. You can generate very, very high amounts of forces using this kind of a device. So, okay, so this is the verbal description of the device. I hope you could understand it. Now let's try to model this, mathematical model of it. We said that the orifice, that the port has an area, port area is A0, okay? Now the flow going through that area, Q, is, if you remember your fluid mechanics, you have an equation, something like this, okay? Delta P is the drop in the pressure. Through this orifice, okay, from here to here. It doesn't really matter. Q is simply P, delta P, for example, is PS minus P1. There is a lot of drop of pressure in this, in the flow from this orifice, so it models that one. And you can write this Q as, if you like, CD times A0, we said is WX, W times 2 times 2 delta P over rho times x. Okay. Now what do we see? We see that this is the discharge coefficient of the orifice. W is the width. Delta P, we assume it to be constant. Rho is constant. So this whole thing is constant. Okay. So we can say that Q is equal to some constant, whatever that constant is, times x. So the flow through the orifice, flow through the port, is proportional to the opening of the port, by the pilot piston. Q is proportional to x. That's what we know. Okay. Now this is the port part of it.
Hocam,
Yes.
we call the port area as the open gap, right? Not the
Yes.
whole.
Yes, yes. It is the gap that is opened by the motion of x.
Okay.
So that the flow goes through that area. Okay.
Okay. Thank you.
Okay. Now, if you look at the piston part, piston is easier to model. We have the piston here. The piston moves with a motion of y, and there is the flow coming in, Q. Okay? And as you see, the motion of the piston has an area of A. As I have told you before, you rewrite the continuity equation, which says that rho times Q mass dot m dot is equal to rho times the A times dy dt. Those cancel. So Q is equal to A dy dt is the equation for the port. Okay. But we know that this is equal to, from above, that this is equal to kx. Now, y is the output, x is the input for our system. So, a dy dt is equal to kx. I can write dy dt is equal to k over a x of t, or integrating y of t is integral, I should say before the integral, I should put k over a, integral x of, let's say, tau theta. So what do we see? The output is the integral of the input. As a matter of fact, if you want to find the transfer function, y of s is simply k over as times x of s. Okay. Now, what does it mean, the output to be the integral of the input? Okay. It means the following. If you, move x a little bit and let it stay there. So it is a step input, okay? This is x of t versus t. What is going to happen? Y of t. This is t, this is y of t. It is going to integrate this It is the area underneath this curve. So this will be increasing like this. So basically, if you push X a little bit, flow starts coming in and it starts pushing the piston, pushes and pushes it. Eventually, of course, the piston comes to a stop. It cannot move anymore, and then it will go on like this. But in this portion, the output is going to be the integral of the input, okay? But then when the physical limits is reached, the equation will not be valid anymore, okay? Still, if you apply a sine wave, for example, the output will be a cosine wave, etc. All these things are possible. Of course, you have to obey the physical limits. There are the physical limits of X and Y. The equations are valid for physical motions. Now, this is a model of our system. Output is the integral of the input, we say. And that's what we get. But this model is a simplified model, okay? So maybe I should say here, this is the, this whole thing is the, why is it simple? Because it just uses the continuity, but it doesn't consider the effect of forces at all. Whether you connect a 1 kilogram load or a 1 ton load, it makes no difference to this model, okay? So we have to consider the forces also. So let's say more complicated model. Takes into account the forces. Remember that we have the piston with an area of A. On this side, we have the P1. On this side, we have the P2, right? Right here. And then this thing is connected to a load here, as you might remember, which is M. And this load might be very high. And this thing, everything moves with a velocity of y towards the left. So what is this model say? The forces should be equal to mass times acceleration. Okay? We will say that P1A minus P2A, the forces on the piston, should be equal to m times y double dot, right? And also, we remember that this thing has to be AY dot equals KX. These two things both have to be satisfied. Well, the thing is, these two equations are not very consistent. You cannot really make them work together. You need a third equation here. You remember we derived this, these two, 1 and 2. They don't work together. We need something else. We need a more complex model for the flow through the flow, let's say, through the orifice. The thing is, P1 and P2, there is no reason why P1 and P2 should be different in this above model, because we didn't consider the pressure drops across the orifices. So Q, the flow coming in, should be some constant times X minus another constant times the delta P. Now delta P being the P1 minus P2, the pressure difference between two ports, between the two faces of the piston rather. Okay. So this is a model with two variables here. Now this is this makes more sense. Here you can do the following.
Hocam, in the first equation, is the mass of the piston neglected?
In the
First equation.
yes. It is rather lumped with the load, okay, if you want. It is neglected, that's true.
Okay.
Because the load has a very, very large mass, the mass of the piston is negligible there. You understand?
Okay. Mm-hmm.
But we have to use this equation for our model, because there is no reason for a pressure difference if you don't use this kind of a model, okay? Now, what happens is, if you look at your original, oops, sorry, what did I do? Original thing. This thing comes with a pressure of PS, goes through here, drops to P1. So at this, at this part, the pressure drop is delta P is PS minus P1. And then on this side, the pressure drop is P2, then it drops to P0. So the pressure drop is P2 minus PO, let's say, okay? And we can show that these pressure drops, if you equate them to each other, you can find that the difference has to be proportional to P1 minus P2. It's not that hard to do that. Yes. But I don't want to go into details of this. Please just accept that as a fact for now, because I don't want to go into it. Let me finish this thing for now. So the equations are as follows. As you remember, P1 minus PA, P1 minus P2A is like delta P times A is equal to MY double dot, okay? That's one equation. Second equation, AY dot is equal to K, well, it's not KX anymore, but C1X, some constant, C1X, minus C2 times delta P, okay? From which we can, well, derive our equations. This is 1, this is 2 now. These are consistent equations. Because now delta P can be modeled. How do you do it? Delta P, for example, from the first equation, M over A y double dot, and you can put it into the second equation. A y dot will be C1x minus C2 times M over A y double dot. Collect the y terms together. C2 M over A y double dot plus A y dot is equal to C1x. C1 and C2 are constants, okay? So this is a more complex model. Here you can take the Laplace transforms and so on. The transfer function y of s divided by x of s is going to be C1 over C2m over as squared plus as, or you can simplify this to be C1a s times it is a second order model. On the other hand, interestingly, if C2 is 0, or if m is 0, this model reduces, let's say, to the simple model. Okay. So this is again, it is an integrator. This, 1 over s term is an integrator term, but it has also some other dynamics because of the existence of the mass. If the accelerations are small, or if the masses are small, you can still treat this as an integrator, okay? But the main purpose of this kind of a device, hydraulic servo motor, as I have said, is to move very large loads with small inputs, with the help of the hydraulic pumps, hydraulic pressures, okay? This is extremely useful. You can, move very, very high loads, even with your tip of your finger. Think about, for example, the steering wheel in your car. You can move the car with very small inputs, and there is a hydraulic mechanism which helps you do that, obviously. It aids you. And the hydraulic mechanism is something like this. Think about it. Most of the hydraulic devices have, small inputs and very large outputs. And they are aided by the hydraulic mechanisms, hydraulic pumps. Okay, let me stop here. So I'll take a break and I'll be back in a while, after 10 minutes or so.